What is infinity? I'm sure most of you have seen this symbol, also known as the lemniscate, before. The symbol is often used to represent infinity. But what does it exactly mean? And when do we say that something is infinite or leads to infinity? The true nature of infinity has been a matter of debate for centuries. From ancient Greeks to Indians to Europeans, each civilization that came across infinity put forth their own theory regarding the concept of the infinite. The infinity symbol itself, or the lemniscate, came into existence in the year 1655 as John Wallis, an English mathematician, used it for a number that he considered endless or infinite. Now, if we take a look at the official definition, then something which is boundless, endless, or larger than any natural number is considered to be infinite. But how do we tell for certain that something or some things are infinite in nature? And are all infinities the same? For example, let's consider the set of natural numbers. It starts with 1, then comes 2, then 3, and so on. Each step, we just add plus 1 to the current number to get a larger number than before, such that there is no end. No matter how large of a number we have, we can just do plus 1 to get a bigger number. Thus, the set of natural numbers has no end. And thus, we say that the set of natural numbers is endless or infinite. But is this true infinity? Is the set of natural numbers really the biggest, endless thing that we have? Or is there something even bigger than the set of all natural numbers? And if the set of all natural numbers is really infinite, then is it the same as other infinities? Let's say the number of planets in the universe. To answer such questions, we need to dive deeper into the infinite. Let us consider the set of natural numbers again. Starting with 1, we can always determine the next number by just adding 1 to the current number. If we add 1 to 1, then we get 2, the next element in the series. If we add 1 to 2, we get 3, the third element, and so on and so forth. At any point with any given number, we are sure about what the next number will be, as we can just add 1 to the current number and get the next number. Such an infinity, where each element can be numbered or where we are certain about the next element, is known as a countable infinity. Thus, the set of natural numbers, as we previously discussed, belongs to this category, as you can assign each number to itself, thereby numbering the whole set. Let me illustrate this with a simple example. You have been selected as the next contestant for the hit show Who Wants to Be a Billionaire? The show consists of a guessing game where you, the contestant, have to guess a number. If you guess correctly, then you get $1 billion. Otherwise, you get nothing. You have unlimited attempts and unlimited time to guess correctly. The host can pick any one number from a given set of numbers. This set is known to you, but the number you have to guess. Let's say the host picks a number from the set of all natural numbers, the same set which we previously said was endless or infinite. Now, your job as the contestant is to guess that one number the host selected from the set of all natural numbers, and you get $1 billion. Some might say this is impossible, as the set of all natural numbers is endless or leads to infinity. How am I supposed to guess that one correct number from an infinite number of possibilities? But there is a simple way to solve this problem. As you have unlimited time and unlimited attempts, you can just simply start with 1 and then add 1 for your next guess and so on. Given enough time, you will eventually guess the selected number and become a billionaire. As you can traverse the entire set of all natural numbers just by starting with 1 and then adding 1, we can say that the set of all natural numbers is countably infinite. But what if, instead of the set of all natural numbers, the host picks the set of all irrational numbers? Well, that would lead us to another kind of infinity. Now, for those of you who don't know, irrational numbers are numbers that cannot be represented as the ratio of two other numbers. That is, if P and Q are two numbers, then their ratio is no irrational number. In other words, irrational numbers are unending numbers like pi, the square root of 2, the square root of 3. Numbers like these are known as irrational numbers, and they make up the set of all irrational numbers. Now that you know what irrational numbers are, let's get back to the show. As previously mentioned, the host picks any one number from the set of all irrational numbers and then asks you to guess that number. Well, now you're screwed, as there is no simple way or algorithm to determine the next irrational. That is, you cannot do plus minus 1 here to get the next element. You might have to return empty handed, but not empty minded, as you've gained the knowledge that such a set of numbers where one cannot be sure about the next element is known as a uncountable set, as there is no way to number all elements in this set or to determine the next number in the series. And it is this set which leads us to an uncountable infinity, an infinity where it's not possible to number the individual elements. The idea of infinity has existed for centuries, and over such centuries, many people have sought to rationalize the concept of infinity. And even though we discussed the countable and uncountable kind, there are still more. As one can say, the concept of infinity is infinite itself. For example, there is ordinal infinity, made up of ordinal numbers. Unlike normal finite numbers like 0, 1, 2, 3, and so on, ordinal numbers are used to represent the infinite. The first ordinal number, omega, represents the position after all finite numbers. Adding 1 to omega brings us to another position. Adding 2 would lead us to yet another position, and so on, leading to ordinal infinity. Then there is also the conflict between potential and actual infinity. Potential infinity describes the common understanding of infinity, considering the set of natural numbers again. If we start with 1 and then keep on adding 1, this would lead us to potential infinity, an infinity that we know exists but can never be reached, no matter how fast or how long we count. Actual infinity, on the other hand, describes infinity as something we know that exists and we just accept its infinite nature. Considering the set of natural numbers again, we accept that the set of natural numbers exists as an infinite entity at once. Both these definitions may sound similar, but are actually quite different, as shown by Georg Cantor, a very renowned German mathematician. Before him, all infinities were considered potential. And then he came along and said that we should accept infinities as they are, and not as some unreachable concept. That is, we accept them as they are, and we accept that all infinite sets exist at once. Cantor did not stop there though. He went on to describe the cardinal hierarchy of infinity. A cardinal number is a number that describes the number of elements in a set. Let's say that if we have a set with 3 elements, then the cardinal number of that set would be 3. For infinite sets, such as the set of natural numbers, it is denoted with the Hebrew letter aleph. Cantor argued that not all infinities are the same. Some infinities are bigger than others. To describe his ideas, he used aleph numbers. Aleph null is the smallest kind of infinity. Subsequent aleph numbers, aleph 1, aleph 2, represent uncountable infinities, each one bigger than the previous. Speaking of big infinities, there exist infinities even larger than infinity itself. The idea, known as infinity of infinities, again proposed by Georg Cantor, describes how, for any given set, its power set, that is, the set of its subsets, has a cardinality greater than the set itself, as the number of elements in a set is infinite. Thus, the power set of an infinite set has infinitely many elements, and it follows that there is no largest infinite set. There are infinitely many sets whose sizes differ. Thus, set of infinites is itself infinite, and there exist infinitely many infinities. Infinity of infinities. Anyways, that was all I wrote. This is AD from Silverlight Studio signing off. I hope you learned something from this video or at least found the video interesting. And if you did, don't forget to like, comment, and subscribe. Each of those motivates me a lot. Until next time.